The coolest effects we're going to look at is the interference pattern associated with thin films. So these thin films can be very thin films of like soap or oil on top of water. You'll see these in parking lots, these beautiful rainbow colors in parking lots where there's a little bit of oil floating on top of the water. So while they are beautiful patterns, it does mean that the environment is contaminated with these oils. So how do these interference patterns occur? Well, these are very thin films, and so what happens is that every time we have a ray refracted, we also have part of the ray is reflected. So one thing that confused me when I first started looking at these is these ray diagrams, this light is going straight up and down, but we can't really draw the rays straight up and down because they'd be straight on top of each other. So in these figures, these rays are going to be drawn at small angles, but really they're coming straight up and down. So one place we see this is coating on glass, so to give it anti-reflective type properties. So if you have glasses, you can order them with an anti-reflection coating and lots of different coatings to change the optical properties of the glass. Also, if we have a solar cell, we want to collect as much light as possible, so we'll put an anti-reflective coating on top of the pure silicon in order to prevent the reflection of light. And so how does that happen? Is that when we're talking about interference with thin films, we have basically two interfaces that we're going to deal with. We have two reflected rays, one off the top interface and one off the bottom interface. If we're going, for instance, from air to glass or plastic, then there is going to be an inversion in that refracted ray. However, if we're going from glass back into air, and we could go from glass into a different type of glass or a different type of material, so it's not always the case. We'll have to look at it. We'll go through that. But in this case, we're going back to air. The refracted ray is not inverted. So we're going to have to watch these on each of the problems to figure out which rays undergo an inversion and which ones do not. So the wavelength of light in the media with the index of refraction is going to be slightly different. So we're going to have to take that into account as well. So here's another example. We have air going through a material back into air. So again, ray 1 undergoes a phase change and ray 2 undergoes no phase change. So when this happens, these are our equations for constructive interference. We're going to use the m plus a half because of this 100-degree phase inversion. So 2nt is basically the thickness of our material, and we got to put an n in there because we have our index of refraction, and that's going to affect the wavelength of light. And m is some integer, including 0, and lambda is the wavelength for our light. And then for destructive interference, we do not have the 1/2 because of that phase inversion from the one ray. And we can see these in pretty rainbow colors. So this is a film of soap hanging from a hoop, and it gets thicker as you go down. So we see a rainbow effect because basically as the film gets thicker because it's falling due to gravity, we can see that that thickness increase corresponds to different wavelengths of light. So two factors influence interference. Is the number of phase reversals, because we don't have to go back into air, and the differences in the distance traveled, so our film thicknesses. So these conditions are valid for the medium above the surface as well as below the surface. So we got to figure out what if we're going into air or water or whatever on the backside. So problem-solving strategy is 1, identify the thin film that's causing the interference. Sometimes it might be water, soap, air, could even be air. So determine the indices of refraction of the film and the media that are on either side of it, and determine the number of phase reversals. It's going to be for this glass 1, 0, or 2. And decide if the interference is constructive or destructive or what we're solving for. So here's a nice handy table, is if there's one phase reversal, then we're going to use this equation for constructive and this one for destructive interference. And if there's an even number of phase reversals, 0 or 2, we flip the equations over because there's either one less phase reversal or one more phase reversal. And those if we have two phase reversals, it basically cancels each other out. Now we're going to look at a problem. We're going to look at the reflection and the refraction of our light. We do know the index of refraction of this particular material is 1.5, and that is more than air. So if we look at our diagram, we have air, film, and then air. So we have exactly one phase reversal, and that's going to occur on the first reflected ray. So we also know the film thickness is 910 nanometers. So we want to find which wavelengths are reflected most strongly. And so those are going to be constructively interfered with, which ones are reflected the weakest, and which ones are transmitted. So we want to find which wavelengths are missing for the reflected light. And so that means we're looking for destructive interference. And with one phase reversal, this is the equation for destructive interference, and this is the equation for constructive interference. So if we rearrange this, we get lambda is equal to 2nt over m, and we have all the numbers but m. So I'm going to plug in the numbers that I do have. 910 nanometers over m gives us 2,730 nanometers over m, and what we need to do is just try different m's until we get in the range of what is visible light, because we can't see the ones that are not. So 2,730 over m is equal to 1. It's just 2,730 nanometers, not visible. Then we go to 2,730 over 3 is equal to 1,365 nanometers, again not visible. 2,730 over, sorry, that was 3 is equal to 910 nanometers, getting closer, but not visible. So all of these are not visible. And then we do 2,730 over 4 nanometers, gives us 682.5 nanometers, which is a red. Then 2,730 nanometers over 5 is equal to 546 nanometers, which is green, and 2,730 nanometers over 6 is 455 nanometers, and that's going to be a purple. So we get those three wavelengths are the ones that are not visible in the reflected ray because they have experienced destructive interference. Now if I went to 7, we would get again outside of the visible spectrum. And then we can do the same exact thing for constructive interference using the formula with the m plus a half, and we get these wavelengths are the ones that we can see in the spectrum. And so if these are for the reflected light, these are the wavelengths we found for constructive interference. So this is the ones we can see. Then we got these ones with destructive interference, so not seen in reflection, but that light had to go somewhere. We know it can't change in frequency because we've already looked at that from refraction. So that light must go somewhere, and that is the light that is transmitted. So the light that is destructively interfered with upon reflection must be transmitted through the bubble. Now it's your turn to give it a try. See if you can figure out how many phase reversals are and if we're dealing with constructive or destructive interference. Hopefully you've given it some thought. We know that the coating has an N of 1.38. The glass is N is equal to 1.5. So I have 2 phase reversals. So I'm dealing with this column. And we want to eliminate the reflected light. So I'm dealing with destructive interference. So my equation is 2nt is equal to m plus 1/2 lambda. And that means if I rearrange it, t is equal to m plus 1/2 times lambda over 2n. And so if I put those numbers in, I get 1/2 times 550 times 10 to the negative 9 nanometers was the wavelength of light given, divided by 2 times 1.38 was my index of refraction in my film, and I get 99.6 nanometers as my film thickness. There you go. Those are the numbers nicely typed up.